Our next example is a variant of an exercise we did a while ago, which is about the 100 numbers. So let's find it again. Here. I'm gonna copy it here just so you can see it again. So we had the 100 numbers, 1 up to 100 written in a row. We were allowed to swap 2 of them that were at a distance of 2. And the question was whether we could just reverse the order of all the numbers using these kinds of swaps. And the answer was no, because numbers that are in odd positions remained in odd positions, and numbers that are in even positions remained in even position. Now, I'm going to replace 100 by 99. And now the goal is the same. Can we reverse their order? And now the argument that we did last time doesn't work, because it's still true that numbers in odd positions remain in odd positions, but that's not a contradiction to the thing we want, because we want them to remain in those positions. This does not mean that the answer is yes. This just means that the reason why the answer was no last time does not apply this time. Maybe it's still no for a more sophisticated reason. Well, but this time the answer is yes. We can do this. And I'm not even going to use a monovariant to prove it. I'm going to use something that we did a while ago using a monovariant. I'm going to use this exercise about sorting a sequence. So I'm going to reuse the monovariant that we used here via this exercise. So how? How do we reverse the order of these 99 numbers? So consider the odd position numbers, which means the numbers in the odd positions, and the even position numbers, so the numbers in the even positions, separately. And as before, positions are counted from the left. So at the beginning, 1 is in position 1, 2 is in position 2, and so on. And 99 is in position 99. But at the end, the positions are reversed. Each move, so in each move, the odd position numbers remain odd positioned, because each number that moves can only move a distance of 2, and that preserves the parity of its position. And the even positioned numbers remain even positioned. Next, and this is another little trick, sometimes known as working backwards. It's useful in various situations. We observe that our moves are reversible. So what are our moves? Our moves are swapping 2 numbers at a distance of 2 apart. And if you do this once, you can do this again and you're back. So swapping 2 numbers twice is the same as doing nothing. Hence, if we can transform a state A into a state B using a sequence of moves, then we can also transform state B into state A using a sequence of moves. And to be specific, this sequence that we are using here is just the reverse of this sequence. We just need to undo all those moves, and we do this by doing them all in reverse. And by state, of course, I mean a way of arranging the numbers on the row. So thus, instead of solving the exercise as it is stated, we can just as well solve the inverse exercise, starting with the numbers 99, 98, and so on. We want to end up, so we want to achieve 1, 2, and so on, 99. So what did we do? We interchanged the starting state with the desired final state. So the final state became the starting state, and the starting state became the desired final state. And as I said, this is okay, because these moves are reversible, so getting from one to the other is the same as getting from the other to the one. How do we do this? Well, let us now look at the odd position numbers. We can swap two adjacent odd position numbers by one of our moves. In fact, so what do I mean by adjacent? So here are the numbers just in a symbolic way: odd position, even position, odd position, even position. And when I say two adjacent odd position numbers, of course, I mean two odd position numbers which are at a distance of 2. So they don't have any other odd position numbers between them. Of course, they will have an even positioned one between them. And when you see two adjacent odd position numbers, you can swap them because they're at a distance of 2, so a move lets you just swap them. So we can swap any two adjacent odd position numbers by a move. However, one of our previous exercises tells us that we can make any, so we can sort any n tuple of numbers, and by sort I mean make it weakly increasing, by a sequence of swaps of adjacent entries. This is this exercise. Actually, it says a little bit more. It says that you can get it sorted by a sequence of at most n choose 2 swaps, and not just arbitrary swaps, but swaps of out of order entries. But all we need is that these are swaps of adjacent entries. So, considering only the odd positioned numbers, we thus see that we can sort the odd positioned numbers by a sequence of moves, because swapping two adjacent odd position numbers is a move in our sense. So the odd position numbers at the onset were 1, 3, 5, and so on 99, because each number was in its own position. But after we have sorted, sorry, I forgot, we were doing the inverse exercise. So they were not 1, 2, they were not 1, 3, 5, and so on. They were 99, 97, 95, and so on 1. Thus, after sorting them, they become 1, 3, 5, and so on 99. Note this does not affect, so this sequence of moves does not affect the even positioned numbers, because they're in between, we're never swapping them. Next, we do the same to the even positioned numbers, because again, even positioned numbers are at a distance of 2 apart when they're adjacent. So we can swap them by our moves, and we can get them sorted. So they were 98, 96, 94, and so on 2 before sorting. After sorting, they are 2, 4, 6, and so on, and 98. And that's important, this sequence of moves does not affect the odd position numbers. So as we have sorted the even position numbers, the odd position numbers did not get messed up. They are still sorted. They're still 1, 3, 5, and so on in this order. Lots of errors are commonly made in such arguments when you kind of try to clean up part of the sequence, and in the process you mess up another part. But here it doesn't happen, because a move that swaps to even positioned entries does not touch the odd positioned entries. So after all these moves, we thus achieve a state where the odd position numbers are, as we have seen, they're just 1 up to 99, the odd ones. And the even position numbers are 2, 4, 6, and so on 98. Thus, in this position, the numbers are just 1, 2, and so on 99 from left to right. And this is exactly the positions that we wanted to achieve in this inverse problem. So the inverse exercise is thus solved. And as we already explained, this also solves the original exercise because the inverse exercise is equivalent to the original exercise. And by the way, you can play this game with 5 instead of 99, which just makes it simpler. So first you have to, the idea is to first get the, okay, so with 5 instead of 99, we start with 5, 4, 3, 2, 1, that's the inverse exercise. Then we get the odd positioned entries sorted. So the 5, 3, and 1. How do we do this? We first swap 5 and 3. Then we swap 5 and 1. 3, 4, 1, 2, 5. Then we have a 3 and a 1, which we still need to swap. 1, 4, 3, 2, 5. And 1, 4, 3, 2, 5. And now you see the odd position numbers are already sorted. Only the even position numbers remain to be sorted. Fortunately, there is just 2 of them, so you can sort them in one swap. 1, 2, 3, 4, 5, and that's it. So we can, so here is how we solve the inverse problem. And thus, for the original problem, we just have to do this in reverse order. So this becomes this, becomes this, becomes this, becomes this. And that's it.